Physics Part 133. Also, the thicker a wire, the smaller its resistance will be. This is because there is a bigger area for the charge to travel through, with less chance of collision. In fact, the resistance is inversely proportional to the cross-sectional area of the wire, or R, to that of I divided by A. These relations are illustrated in figures 7.1 and 7.12. We'll continue with it. Finally, the resistance depends on the type of material, as previously stated. Copper is a good conductor, whereas plastics are good insulators. Putting all of this together gives R is equal to Pi over A, where P is a constant for a particular material at particular temperature. P is called the resistivity of the material at that temperature. The resistivity of P of a material is numerically equal to the resistance between opposite faces of a cube of the material of unit length and unit cross-sectional area. So if P is equal to RA over I, and the resistance in the ohm, the cross-sectional area in meters squared, and the length in meters, then resistivity is in ohms meter, omega m. Remember that A is cross-sectional area through which the current is passing, not the surface area. We have already seen the resistance of a wire depends on temperature, thus resistivity also depends on temperature. The resistivities of metals increase with increasing temperature, and the resistivities of semiconductors decrease very rapidly with the increasing temperature. The values of the resistivity of some materials at room temperature are given in a table here. Metals: copper 1.7 into 10 power raised to minus 8, gold 2.4 into 10 power raised to minus 8, aluminium 2.6 into 10 power raised to minus 8, semiconductors, germanium pure 0.6, silicon pure 2.3 into 10 power raised to plus 3, glass about 10 power raised to 12, perspex about 10 power raised to 13, polyethylene about 10 power raised to 14, sulfur about 10 parts raised to 15. Now, the enormous range of resistivities spanned by the materials in this list, a range of 23 orders of magnitude from 10 power raised to minus 8 omega m and 10 power raised to 15 omega m. Note too that the resistivity is a property of the material, while the resistance is property of a particular wire or device. We have an example for you. Calculate the resistance per meter at room temperature of the constant wire of diameter 1.25 millimeter. The resistivity of the constant at room temperature is 5 into 10 power raised to minus 7 omega m. You can solve it. The answer is 0.41 omega m. Now it's your turn. Find the length of a copper wire of diameter 0.63 mm, which has a resistance of 0.1 1.00 omega. Find the diameter of a copper wire which has the same resistance as that of the aluminium wire of equal length and diameter 1.20 mm.